In Unit 2b, again we're stressing that Lewis structures are not sufficient to describe molecules. At least two models for molecules are necessary: a molecular orbital model and the Lewis structure. Double bonds in Lewis structures need to be translated into molecular models. There are two ways to form a bond in organic chemistry: sigma and pi. We're also going to discuss about molecular orbital energy diagrams and say something about what we can get from these diagrams in terms of chemical information.
Occupied orbitals react with unoccupied orbitals. Occupied orbitals of the highest potential energy are used as bases. Unoccupied orbitals of the lowest potential energy serve as Lewis acids.
The addition reaction and the elimination reaction are opposite processes. Let's unite this concept with what we have so far. When we considered the sigma bond between the two hydrogen atoms in molecular hydrogen, we basically said that the Lewis structure of molecular hydrogen did not tell the whole story about the chemical reactivity of the molecule. It's hard to show electronic excited states with Lewis structures. You can't show antibonds with Lewis structures. And another function of the antibond occurs when it accepts an electron from the bond, when the molecule is promoted to its electronic excited state by light, electromagnetic phenomenon. In this case, the antibonding molecular orbitals are populated. These are next up in energy from the sigma bond between the two hydrogen atoms. If we add an electron to molecular hydrogen and get hydrogen molecule minus with an unpaired electron, that unpaired electron is also going to go in the antibonding orbitals. In both of these species, the excited state of hydrogen, we have an occupied antibond, and in the reduced hydrogen minus, we have an occupied antibond. But the Lewis structure does not even show the antibonding molecular orbital, even though its chemistry is necessary to describe that of the hydrogen molecule. Let's consider the Lewis structure of C2H4.
Because double bonds further stress the need for an orbital picture of the molecule. We get 8 valence electrons from the 2 carbon atoms and 4 from the 4 hydrogen atoms. That gives us 12. Since the structure is neutral, there are no more electrons to add or subtract from the count.
So after we connect the bonds, we have 10 electrons involved in 5 bonds, and we have 2 electrons to add to the structure, and we simply add these 2 electrons to the carbon atoms. These 2 added electrons are going to make a bond. We conceptualize this in the new CC interaction as a double bond. Even though the Lewis structure indicates that these 2 electron pairs involved in bonding are exactly the same, experimentation indicates a great difference between the chemistries between these 2 electron pairs. Putting these 2 electron pairs between the 2 carbon atoms is impossible. Electrons are fermions, cannot have the same quantum mechanical descriptors. In this case, each pair would have to have at least 2 electrons with the same quantum mechanical descriptions. To get around this, early descriptions framed the double bond as a 2-membered ring, a strained ring. Eventually this description failed as well. What's going to follow is a modern view of bonding of the first 3 rows in the periodic table. Basically, between these atoms, there are 2 ways to form a bond. 1, head-on, and this we call sigma, and 2, parallel, and this we call pi. These 2 bonding motifs depend on the disposition of the orbitals that are interacting. Let's discuss this further. First, let's consider the head-on interaction. From now on, I'm just going to call this sigma bonding. In the second row and the third row of the periodic table, all these atoms and their electrons are going to have p orbital character. So, unlike the construction of the hydrogen atom in which we used s orbitals, we have these dumbbell-shaped constructions. But very much like the construction of the hydrogen molecule from hydrogen atoms, we have a collaborative interaction, which is a sigma bond, and a destructive interaction, or a non-collaborative interaction, which is a sigma antibond. The sigma MO gets populated, and the sigma star MO, or the antibonding MO, remains unpopulated. Note that there is a node, a region of no electron density in the sigma star orbital. This is exactly the same as the construction for the hydrogen atom that we went through earlier, except that we have these dumbbells. All this, of course, is due to the fact that matter, when it's very small and very fast, behaves in a quantum mechanical manner. Simply put, the electron has two phases. When the phases match, the electron behaves constructively, and it is easier to find in the spaces in which they match. When the two phases mismatch, the electron disappears. It is impossible to find. It does not exist in these regions. We call these regions nodes. The red side and the blue side of these orbitals represents the negative and the positive aspects of the matter wave for the electron. And again, these are orbitals, so they describe where the electron can be around the nuclei. The black dots in the diagram are nuclei. Let's compare and contrast sigma bonding to pi bonding. Of course, there are going to be similarities, but there are going to be important differences as well. Just like when we formed the sigma MO, when we form the pi MO, we construct a pi MO constructive interaction between the two p orbitals, or p-like orbitals, of any atom in the second and third row of the periodic table. We have a destructive interaction that makes pi star, and of course the electrons end up in the pi MO, and the pi star MO remains empty. We start with two atomic orbitals and make two molecular orbitals, pi and pi star. Just like the sigma interaction in the antibonding orbital, the starred orbital, there is a node, a region of no electron density between the two atoms in the antibonding orbital. Well, I highlighted the similarities between the two bonding motifs, pi and sigma. Let's focus now on the stark differences between pi and sigma. Parallel versus head-on, of course, is an obvious difference, but the major difference comes in stabilization energy. In the sigma MO, the populated sigma orbital become more stabilized, of lower potential energy, and sigma star becomes destabilized. When we're making an account of the electronic stability of the molecule, we are only focusing on the occupied orbitals. So the formation of a sigma bond is stabilizing the molecule greater than the formation of a pi bond. Of course, the pi occupied orbital is stabilized less, it contributes less to the molecular stability, and the pi star orbital is destabilized less. We don't count it because it's empty, but we will have to take it into account if we consider it as a place for electrons to go in a chemical reaction. By the way, CH2 with two electrons is called methylene, and this word in terms of nomenclature is going to pop up again, so you might want to commit it to memory. Now you can see how the two lines in the Lewis structure are, well, obviously different. One is a parallel interaction, a pi interaction, and the other is a head-on interaction, a sigma interaction. Their energies are extremely different, and the way they stabilize the molecule as well is very different. In the preceding, I brought two methylene molecules together to make the molecule ethylene. When these two fragments approach each other, their molecular orbitals change in energy and they form sigma MO, pi MO, pi star MO, and sigma star molecular orbital. We are following the rules of molecular orbital conservation because 4 molecular orbitals made 4 molecular orbitals in this transformation of molecular orbitals. The molecular orbital energy diagram shows how each molecular orbital contributes to molecular stability. It also shows what the energy of an extra electron in a molecule would be if the electron is added. Our discourse is coming around kind of full circle here. Remember, this is an alkene. In fact, it's ethylene. This is the product of the elimination reaction. Remember, in the elimination reaction, we had a hydrogen and a leaving group positioned 1, 2 relative to each other.
In the elimination reaction, the carbon atom at position 1 served as the proton donor.
A carbon acid. That process permitted the leaving group to depart. You're going to learn that Mother Nature aligns the sigma bonds in a parallel fashion in order to be able to most efficiently form the pi bond across the two carbon atoms. With the view of the molecular orbitals in mind, we have almost a secret window into the chemistry of the alkene, the product of elimination.
When the base takes off the proton at carbon atom 1, this carbon atom becomes partially negatively charged. And then we establish a parallel interaction, a pi interaction between the orbital at carbon 1, containing the lone pair, and the sigma star orbital of the carbon leaving group bond. This parallel occupation of this sigma star orbital by the lone pair, the parallel occupation of this sigma star orbital by the lone pair, is an occupied/unoccupied orbital interaction, and this is the definition of a parallel bond. Remember that occupation of the sigma star orbital destabilizes the bond between the two atoms the sigma orbital is holding together.
Similar to the questions regarding the hydrogen molecule, the question might be asked, where does the electron go in a one electron reduction of ethylene? Which molecular orbital accepts the electron? The answer is that the electron goes in the lowest energy unoccupied orbital. In this case, it's pi star. Pi star is the electron acceptor. As a further demonstration to how you can use Lewis structures and molecular orbitals together, the question might be asked, which molecular orbital does the proton react with? Let's pretend X minus is very stable and does not react. Since the proton is an acid, it is seeking electrons. It will seek the highest energy electrons and leave the lowest, most stable electrons alone. I want you to draw your attention to something else. When I splayed out the sigma, pi star, and sigma star molecular orbitals in energy, I intentionally ignored the carbon-hydrogen molecular orbitals. These would be in the molecular orbital diagram as well. I'm just not showing them because I just don't want to complicate things. In any case, pi contains electrons that are higher in energy than these CH sigma bonds. When a proton reacts with the carbon framework, it accesses the pi molecular orbital, switching the positive charge from the hydrogen atom to the carbon atom. Now we have a place for the X minus, this really stable anion, to just stick to. By the way, this is the addition reaction, and it is the phenomenological reverse of the elimination reaction. One of the points to all this, of course, is we just can't use the Lewis structure as the only thing in our mind in order to model what's going on in a reaction in which the pi bond is reacting with a proton and addition is occurring across the double bond. Sure. The pi bond is reacting, but we have to think in terms of molecular orbitals, and the proton reacting on the face of the carbon-carbon double bond with the pi orbitals in a head-on fashion to make a sigma bond between carbon and hydrogen, and then the chloride atom can make a counterattack onto the electron-deficient carbon atom and form a sigma bond between carbon and chlorine. We have to be thinking in terms of molecular orbitals and bond formations in order to make a more realistic picture, more realistic model of the chemistry that is occurring. And you're going to have to do this in organic chemistry as well. There are two models to bear in mind. The first model really is molecular orbitals, and it adds an air of realism to the Lewis structures that we draw. Ignoring molecular orbitals and only going with Lewis linguistic approach to organic chemistry is the biggest mistake that students often make, and why they have trouble understanding the arguments in organic chemistry.
The first step in this journey is to see how molecular orbitals dictate chemical reactivity. After that, we're going to talk about how MOs mandate molecular geometry.